We're going to go ahead and look at that example I suggested, the uh, line of intersection of two planes. We'll write that out here. See what we get. So we'll go ahead and start with the problem here. We'll take two planes. One I'll give as 3x plus 2y minus 4z minus 6 equals to 0, and maybe x minus 3y minus 2z minus 4 equals to 0. So we notice that with two planes, we essentially get two equations, three unknowns. We know from our experience that two equations, three unknowns, this is going to be an infinite solution of some sort, right? It's not going to be a unique solution. So let's take a look at what that actually means for our problem. So if I put this into kind of a format, I'm going to add a row of zeros because I know that if we were working this before, we would want to write three equations and three unknowns. That's going to make our life easier. Another step that I'm going to work at here to make this a little easier on us is I'm going to actually transfer this into the normal format. So I'm going to have 3x plus 2y minus 4z equals to 6, 1x minus 3y minus 2z equals to 4, and then I'm going to have 0x if you want, 0y, 0z equals to 0. That way I can write the following matrix down, which is a little more corresponding here. Let's take that away. So I'll get 3, 2, too close there, 3, 2, minus 4, 6, 1, minus 3, minus 2, 4, and then 0, 0, 0, 0. And I'm going to do reduced row echelon on that if you want. You could do it on a calculator like this. I only chose 2 rows on my calculator because that's quite sufficient for doing this. So if we do reduced row echelon, we can reduce this to 1, 0, 0, 0, 1, 0. Certainly the first two columns are pretty simple. Minus 16 elevenths for this part here, 2 elevenths for the next value. This last row remains to be 0. This will be 26 elevenths for the coefficient on that side, and minus 6 elevenths for the coefficient on that side, and a 0 on the bottom row is expected. So that's what I actually get for my reduced row echelon matrix. Now I'm going to write this like we wrote before as a linear combination of matrices. So I'll do, or vectors more precisely. So I'll do 1, 0, 0, x, and then 0, 1, 0. I'll do that for y. I'll do 0, 0, 1, and in this case, trying to do that for z. But if I do that for z, I still have the leftover that I have to have. So I'm actually have another part of z here. I'm going to have that minus 16 elevenths here. And then I'm going to have the 2 elevenths and the 0. So I actually have two z's here because I got that extra piece. And on this side, I'm going to have the equals. And then on the equals, I'm going to have 26 elevenths here and minus 6 elevenths and 0. So I have this kind of extra awkwardness here because of that part that isn't actually 0. So this is where I'm going to make the step to parameterize my solution. So I'm going to actually parameterize it. Before I do that, though, I'm going to actually move this over to the right, so I'll have something a little cleaner. So I'll have 1, 0, 0, x, 0, 1, 0, y, and then 0, 0, 1, z. I'll move everything over to this side, so I'll have plus 16 over 11 minus 2 over 11, 0 here, z, and then I'll have plus 26 over 11 minus 6 over 11 and 0 here. So I'm choosing to write the standard way of writing the linear combination. Notice I'm using the unit values, the 1, 0, 0, 0, 1, 0, 0, 0, 1. They surprisingly correspond to I, J, and K, surprisingly. And if you remember when we did the linear combinations, this linear combination is actually going to be the column vector x, y, z. And this part here is going to be, I'm going to choose a parameter. I'm going to say let z is equal to t. So that's my parameterization. So I'll have 16 over 11 minus 2 over 11 and 0. So that's the parameterization of t. And then notice this will simply be the leftover part, 26 over 11 minus 6 over 11, 0. Notice that this actually gives me a great description of what's going on. This is my line in R3. And notice it's pretty similar to the kind of a line that we might have in R2. In the fact that what we have here is essentially an expression of the line x, y, z with a vector here that actually describes the direction with the parameter t. So what I get here really is this parameter t. This is my direction vector. And it's a direction vector of parameter t plus, and this part over here, this is not a direction vector. This is actually the initial point of this line. So what I have here is an initial point, an intercept, if you will, and a line. So my equation of my line actually looks like that. That it's x, y, z equals to this. This is the direction of the line. So if you want, that gives me a vector direction of the line, and p naught gives me an initial point. So now that I've got a point on the line and its direction, I can really establish exactly where in R3 this line is. And to give another feeling for that, if I was to go down here and talk about that line in R3, what does it really mean? Well, let me draw this back in. If I took the plane, this is the first plane, and the first plane has that line in it. And if you take that drawing here and I draw the second plane might be in this established, this kind of thing. And you see that the blue line is actually the intersection of the two planes. So the intersection of two planes actually is a line in 3 space. And not only is it a line in 3 space, but we can see it's a line in 3 space that we can describe readily as in vector format as a vector with direction d, point p as the initial one. And I'm just going to add to this something that we didn't quite put in there. We remember this parameter, the t, is an element of real numbers, and that's where we get the infinitive from. So we get from minus infinity to t to positive infinity, that this actually is a line that goes all the way to the left and all the way to the right here, following that direction with initial point p. It's a very interesting result. It's a very important result. It takes advantage of our linear combinations. It takes advantage of our vectors, and it takes advantage of the different ways of writing the system. Okay. You can do the same kind of expression without these third row, and you'd end up expressing this also as a vector. You just would have an odd way of writing it with x, y, z, but it's still expressible that way. So by doing these matrices and these vectors, we start to introduce a lot of different ways of expressing essentially the same thing.